Well, that's what they say. Like if you're in Hattiesburg, you don't like Weber, wait 10 minutes.
Yeah.
Okay, so we're going to finish up polynomial approximation in the 2 norm. Okay. Now, so just a quick recap. Okay. So the problem that we're solving is find a polynomial, p sub n, such that the error, so basically Pn is meant to approximate some function f, so that the 2 norm of the error is minimized. And unlike for the case of the infinity norm, we have an actual solution where the 2 norm of a function is the square root of the inner product of a function of itself, and the inner product is integral from a to b and we've been assuming our functions are real, but in case they're not, I'm putting complex conjugate. And then we have some wave function specified. And the solution is sum of coefficients times some orthogonal polynomials where each coefficient is just the inner product of one of these orthogonal polynomials with f over inner product with itself. Okay. Now, so I mentioned one kind of orthogonal polynomial family.
Hey, I got a question real quick. Are you saying that that's inner product of f and g is equal to Pn of x equals the sum, or is that?
Wait a minute.
What does that is come in from?
Oh. Okay. Oops. Okay. So if we're solving this problem, the solution is okay. Yeah, like once you maybe look at it, like, yep, it really doesn't make sense. Okay. All right. So as an example of families of orthogonal polynomials, if the interval is -1 to 1, and the weight function is 1, that leads to the Legendre polynomials. I talked about some last time. Okay. But today I want to focus on another family of orthogonal polynomials that we've actually brought up before, but I want to throw in something extra about it. And that is the good old Chebyshev polynomials. So, if the interval is again -1 to 1, and the weight function is 1 over square root of 1 minus x squared, which seems like an odd choice because it is singular. It blows up at the endpoints, -1 and 1, but it still works as a weight function. Then that produces the Chebyshev polynomials that are orthogonal with respect to this weight function on this interval. I've used t before, I'll stick with that. Cosine j inverse cosine of x, at least on the interval -1 to 1, but we don't really care what it would look like outside of that interval anyway. you can extend it outside minus 1 to 1 if you use hyperbolic cosine instead of cosine. Okay. Now, so one interesting thing I want to point out is, so suppose we're using this interval in this weight function, so if we're going to expand our function f of x in terms of Chebyshev polynomials, then the coefficients that we need to compute so that's going to be the inner product of each Chebyshev polynomial with f over Chebyshev polynomial with itself. And let's take a look at this integral. So that would be the integral from minus 1 to 1 of tj of x, f of x, times a weight function. Okay. But now I want to fill in what the definition of tj of x is. So that's going to be cosine j inverse cosine of x, f, over square root of 1 minus x squared. Now this integral looks like it would be a pain to compute, but we can actually make it a whole lot easier making a substitution. So the substitution I'll make is let x equal cosine theta. So what happens in that case is dx, well, let's see, actually, all right, I'll do it this way. So dx would be minus sine theta d theta, but I can express sine as, so, okay, minus square root of 1 minus cosine squared theta, but the cosine theta is x, so that means that d theta is equal to minus dx over square root of 1 minus x squared. So that's convenient because then all of this just becomes minus d theta. Also, if I take a look at this, if x is cosine theta, then inverse cosine of x is just theta. So that part simplifies. And then the limits are minus 1 to 1 in x, but that corresponds to the angles 0 and pi. So for theta, so I can write this as the integral from 0 to pi of cosine j theta f of cosine theta d theta. So now the integral simplifies quite a bit. Now what I did here, because 1 is cosine of 0, minus 1 is cosine of pi, but I had a minus. So I swapped the limits to go from 0 to pi instead of pi to 0, and that gets rid of a minus. So I glossed over a couple things to arrive at this integral. But what this is, when you're taking inner product with just a cosine of an integer times your angle, so this is the Fourier cosine transform of f of cosine theta. So in other words, this is very easy to, this can be done very quickly in code. Because what you could do is, you can evaluate f not at equally spaced points in x, but equally spaced points in theta. So in other words, you're evaluating f at Chebyshev points. And you can take the fast Fourier transform of this vector, and there's a little more involved than that, just to do a cosine transform. The point is, to get the coefficients, the CJs, for j equals 0, 1, 2, up to n, in this case would take on the order of n logarithm to base 2 n flops, or floating point operations. And that's because you're able to take advantage of a fast Fourier transform. Now, by contrast, if you had any other family, or most other families of orthogonal polynomials, normally you have to expend n squared operations, because you're having to compute n plus 1 inner products from degree 0 up to degree n. And then for each one, you're approximating an integral, and that means you're evaluating these functions like order n times usually. So thus resulting in a quadratic amount of work. But if you have a situation like this, because of the symmetry of sine and cosine, you can cut the work down quite a bit. So that's one particular advantage of Chebyshev polynomials compared to other families of orthogonal polynomials. Okay.
What was flops again?
Oh, floating point operations. Yeah. Okay. So certainly by the time you get to the end of this course, you realize, wow, numerical analysis people really, really like Chebyshev polynomials, but there's a lot of reasons to. And this is just one more. Okay. In fact, so these functions, like cosine of j theta or sine of j theta, they're often referred to as trigonometric polynomials. Okay. Which seems a little odd, but when you think about how cosine j theta and sine j theta are the real imaginary parts of e to the I theta raised to the j power. So that's, if you think in terms of complex exponentials, it looks more like what you think of normally as like a literal polynomial. So the term is not as off base as it might seem. Okay. So question about these manipulations of Chebyshev polynomials. All right.
I don't understand how this name came from, trigonometric.
Oh, so instead of having like regular polynomials like 1x, x squared, x to the j, you think in terms of e to the I theta, e to the 2I theta, etc., e to the I theta raised to the j. So these are often referred to as trigonometric polynomials. So you're just raising something else to the j power. But the real and imaginary parts is equal to cosine j theta plus I sine j theta. What?
You said the real imaginary.
The real imaginary part.
Oh,
She was just laughing.
oh, I left out the and. Yeah.
Sounds like enough.
Yeah. Oh, okay. Yeah. Real and imaginary parts. Yeah. Okay. Yeah. So it's a bit of a stretch, but not that much. Yeah. But also, these functions are also orthogonal, which is quite nice. Okay. But yeah, the fact that Chebyshev polynomials, because they can be expressed as cosines, can be bounded by plus or minus 1 on an interval. That's how we use them to our benefit for polynomial interpolation, and that's exploited in many ways.
No, I mean by tree means that diagonal, the one before it and the one after it, we have some elements there.
Oh, tridiagonal?
Oh yeah. Different?
Completely different.
Okay.
Okay. All right. Okay. I'm glad we cleared that up. Yeah. So yes, there'll be other try words you'll run into.
I just thought maybe it's just because of root things.
Oh no. Okay.
Okay.
Although these tridiagonal matrices do have eigenvalues related to cosines and sines, so if we're not careful, we really could find connections. But okay. All right. Okay. So that's all I have for now about Chebyshev polynomials. Although I'm sure that by the time the class is over, we'll see them yet again.
You know, it's like,
I know,
wow.
so it's really dirty, yeah. He said, well, that's all I have for now.
I thought we were about to, like, oh, we're done.
We all thought you were like,
Using
using class.
No.
By that first line, yeah.
Oh. No. You wish, I know.
Right.
Oh, what a funny day this is. Okay. No, I still have. Oh, wow! I have more than I thought. Might take a whole while after all. Not that I'm going to try to. But, okay, we're only 25 minutes in, so plus I started late. Okay, so I have various things to prove. Okay. Don't need that. Okay. Now, so let's suppose that Pn, well, I have something different in my notes though. Okay. Fn be the degree n best two norm approximation of f. So I've been using Pn to refer to it before, but just for consistency of my notes, I'll call it Fn. So that means that Fn is equal to, let's see, I want to express this as a linear combination of polynomials that are not only orthogonal, but they are orthonormal. Whoops. That should be, sorry, these K's should be J's. Okay. All right. And that's why, because they're orthonormal, these are the coefficients, Cj, that I wrote down earlier, says now they don't have to have denominators, because those denominators would be 1 anyway. Okay. So now, I'm going to let P be any polynomial of degree less than or equal to n. So in other words, it's within the space of polynomials of degree up to n. So what I'm going to do is look at this inner product of the error with P. Now, I can, by the linearity of the inner product, I can write that as inner product of f with p minus inner product of fn with p. Now, I can express, well, let's see. can express P as a similar linear combination of QK inner product of QK with P. Now, P is a polynomial of degree up to n, so this is exact. Whereas, and also Fn, also degree up to n, so this is exact. Whereas F, that kind of sum would only be an approximation. So I'll go ahead and dump this form of P into here. So I have QK times the inner product of QK with P. And then over here, I can replace both Fn and P with their representations in terms of the cubes. So Fn is sum Qj, Qjf, and then here we have for P, QK, QKP. All right, so now what I want to do is try to simplify this as best we can. All right. Now, I can use the linearity of the inner product because I can pull out sums and I can pull out constants. So I have a sum of QKP, and then I have the inner product of F with QK. And then on the other side, I have two sums I can pull out. And I can pull out these constants, Qj with F, QK with P, and then what's left is Qj, QK. Now these polynomials are all orthonormal. So this is equal to delta jk. So it's equal to 1 if j is equal to k and 0 otherwise. So in this double sum, all the terms, like all the terms in this sum, j 0 to n, are going to go away except for when j is equal to k. Also, the inner product is commutative. We're talking about real functions. So I'm going to reverse this one. So I have QKP, QKF, minus sum over k, QKF, QKP. So what happens?
That's on that part right there, that Q sub j, comma Q sub k, the inner product.
Yeah.
Okay, that's the only part that's equal to 0, right?
Yes.
Not the whole thing.
Right. But yeah, it's going to cause so many terms to go away.
Right.
So what do I end up with?
0.
Yeah. What's so funny is what I have is when I have students, like if I assign them a problem that's a big long thing to work out, and the answer is something really simple like 0 or 1, I get outraged. Like, oh, that for just for 0, and professors love that stuff. So, so those of you who become, or if not already are teachers, hopefully come to appreciate that in time. But, now, what does this mean? It means that the error is perpendicular to the whole space Pn. Because you're trying to find the best approximation into space Pn, all polynomials of degree less or equal to n. And this is what characterizes the best approximation. That the best approximation should have no component, the error should have no component in that space. It's in whatever error you have resides in the set of higher degree polynomials. And I can actually visualize this for you in another setting where you're trying to find best approximation of, like, instead of functions, just ordinary vectors. Like if I have this vector in the plane, this will play the role of my f. And I want to approximate it by a vector in a certain one-dimensional subspace. So, okay, make sure I get this right. So I have a direction, which I'll call Q. So I want to find whatever multiple of Q will best approximate F. Well, what is that multiple? I'm going to look at the difference between them. And sorry, I need to adjust my picture because I'm running into my overwriting here. Okay. So whatever multiple is going to minimize this distance is the one where the error is going to be perpendicular. So it turns out this, so C times Q, where C is equal to inner product of Q with F, so in this case it's the ordinary dot product, times Q. This is the term used in calculus 3 is vector projection of F onto Q. So what minimizes the error, the distance, is to drop a perpendicular. So if the error is orthogonal to, I totally messed this up, didn't I? Yep. My picture's bad. The error is supposed to be orthogonal not to F, it's supposed to be orthogonal to Q. So I knew something was wrong. Okay. Yeah. So this vector just going out this direction is multiple. So this is the error. And this angle has to be a right angle. Okay. All right. So if the error is orthogonal to the space onto which you're projecting, so Q, or the span of your orthogonal polynomials, that is when you know you have a best approximation. Now, what I've shown right here is if Fn is the best approximation in the 2 norm, then the error is orthogonal to all polynomials of degree less than or equal to n. But sorry about this. I hope I didn't cause confusion. Okay. You don't remember doing this in calculus? Okay. Maybe. Okay. Well, I guess it depends on where you took it. Okay. So what I can also do is prove a converse in a way. If we know that Fn, the error f minus Fn is orthogonal to all polynomials of degree n or less, is that really the best approximation? No. Actually, and if only to redeem myself a little bit, this is a case of projecting onto a one-dimensional space. If you have a vector in three-dimensional space, and you want to find a point in the plane, this plane would have is a span of two vectors, and you want to find the point in this plane that best approximates, so this is your f. Then you drop a perpendicular to the plane. So this is a vector that, such that the error, so this vector right here is your approximation. I'll call it f2 because we're approximating in a two-dimensional space. So, so again, dropping a perpendicular, but this error is perpendicular to the space where you're using for your approximation, in this case, the entire plane. And in fact, if Q1 and Q2 are orthonormal, you can say that F2 is equal to Q1 dot F times Q1 plus Q2 dot F times Q2. If Q1 and Q2 are orthonormal. So if you have two perpendicular unit vectors that describe this plane, you can use them to get the best approximation. And you see, this corresponds exactly to what's going on here. I'm taking inner products of the vector I'm approximating with my basis vectors, it's just that these vectors are now functions, and summing them up, however many dimensions that you have. So it's important that you recognize the parallel between these situations, one dimension, two dimensions, n plus one dimensions. That doesn't matter what kind of vectors you're talking about, vectors in Rn or vectors that are functions. If they're orthonormal with respect to whatever inner product, this is how you find the best approximation limited to a certain space. This one is used all the time for if you have some 3D object and you want to project on a two-dimensional space for visualization, then this is how you do it. Okay. Now, so for a converse of what I just showed here, so if f minus fn is orthogonal to p for all p in your space of polynomials of degree up to n, is fn the best approximation within Pn? Okay. So the thing is, P minus Fn, both of these are polynomials of degree up to n. So they belong to that space. So what I can say is F minus Fn, inner product with this has to be 0 because the error is orthogonal to all polynomials in this space, no matter what they are. But now what I can do is I can expand this using properties of the inner product. So I can have, I don't want to expand it too much. Oh, yep, I don't want to do that. Okay, so F minus Fn, and then I'll use the add subtract trick. So P minus Fn plus Fn minus F. Okay, so, nope, that's not what I wanted to do. Just add subtract F. Okay. So now I can write this as F minus Fn, inner product with F minus Fn. so itself, plus f minus fn with everything else, which would be p minus f. Okay. Now, this is the norm of f minus fn squared. Okay. And then, okay. So now what I can do is take this and move it to the other side. So this would be f minus fn, and I have to negate this. So this is f minus p. Now, here I can use the Cauchy-Schwarz inequality. Which says that this inner product is less than or equal to the norm of one times the norm of the other. Okay. So now I can say that norm of f minus fn squared, oh, these are two norms, is less than or equal to the norm of f minus fn times the norm of f minus p. But now what I can do is I can cancel a norm of f minus fn on both sides. So I have norm of f minus fn less than or equal to norm of f minus p. So that means that if this is true, then fn has to be at least as close to f as any other polynomial in the space. Therefore, it's the best approximation. Okay. Any questions about that?
When you moved over the f minus fn inner product of p minus f, it's not negative because you pulled a negative out and switched f and p?
Right, yeah, so this accomplished the negating I needed to do, yeah. Okay. Any question? Okay. One more thing to prove, because I'm on such a roll. Plus, it's fun to prove things about orthogonal polynomials because things about them always work out so nicely. Kind of like linear algebra. Now, so this is about the roots. I'm going to put a piece of chalk in this because this is darker than that. Not much better. About the roots of orthogonal polynomials. Okay. And this is going to be very important for what we'll use orthogonal polynomials for the next chapter, which is Gaussian quadrature. And, well, 3 or 4 of you are in the KSS, so this is good to know anyway. All right, so let's suppose that if polynomial phi j that's orthogonal to all polynomials of lesser degree. All right, so we assume that it's by the subscript, it has degree j. And we'll assume the degree is greater than or equal to 1, because at least that way it's going to have a root. Otherwise, it would be a constant function. Okay. And let's suppose that the inner product is just a generic one on some interval AB with some weight function. Doesn't matter what it is. Okay. Now, I need some definitions here. So I need these points, C1, C2, up to squiggly K, be the points in the open interval AB. So excluding the boundaries, at which phi j changes sign. So certainly if it has a root at those points, and not a double root, so we're talking simple roots. Now, phi j has degree j, the number of points is k, but we don't know how k and j relate to one another yet. Now, I need to make another definition. And we've seen this sort of thing before. Pi k of x will just be the product of all these linear factors involving these points where it changes sign. Okay. Now, within AB, because all these have to be distinct. So, all right. Now, I should mention this set of points where it changes sign cannot be empty because because it's orthogonal to all polar limits of lesser degree, that would imply that phi j is orthogonal to 1. So the integral itself of phi j by itself has to be 0. So in other words, phi j inner product with 1 has to equal 0. Now, this weight function has to be greater or equal to 0. So phi j has to be both positive and negative within the interval. Otherwise, there's no way this integral could be 0. So it has to have at least one root in AB to give positive area, negative area that will cancel each other out. Okay, so this, I'm just making this point to say that this set of points, these squigglies, is non-empty. So then I can go ahead and define this. Now, phi j and pi k change sign at the same points within AB. So what that means is, if I multiply them together, phi j pi k, this function does not change sign at all in AB. So it's going to be always non-negative or always non-positive. Because basically, you're canceling out the sign changes. Okay. Now, I'm going to use this to figure out what is k. How many of these points are there? So there are three possibilities. Either k is strictly greater than n, k is strictly less than n, and k is equal to n. Now, no, not n. I don't even have an n. J. I need to say that. Okay. All right. Now, can anyone tell me why it's impossible? Why this first case is impossible? Because Vj has degree j, so it tells you something about how many roots it can have.
Can only have j roots.
Yeah, so it can't. Yeah, so it can't change sign more than j times. So that's out because you have too many roots. Okay. Now k less than j, that's a bit more interesting to look at because that would mean that the degree of pi k is less than a degree of phi j. So what does that tell me about this integral of pi k pj with the weight function? So what must I conclude from that?
Zero,
Yes, because
it's orthogonal
to all polynomials of lesser degree. Yeah. All right. So think, okay, no big deal, except for one thing. This whole thing cannot change sign on the interval because all the sign changes have been canceled out. So we conclude simultaneously that it's equal to 0 because of orthogonality, and not equal to 0 because it doesn't change sign. So big fat contradiction. So that is out too. So there's only one possibility left, that k equals j. So this leads to a very interesting conclusion and very helpful conclusion about orthogonal polynomials. So in words, because in general, a polynomial of degree n can have at most n distinct roots, but it has n roots as long as you account for multiplicities, repeated roots, the roots can be complex. But not here. The roots of an orthogonal polynomial, so in other words, any member of a family of orthogonal polynomials, are real, so you don't deal with complex conjugate roots. They are distinct, so there are no repeated roots. Also, depending on what interval you use for inner product, AB, they lie strictly in the interior of AB. And this is why orthogonal polynomials, because we're going to use them later for Gaussian quadrature, we're going to use the roots as the nodes. Well, the nodes ought to be in AB, but now we know they are. And we don't get any other complications to having complex roots or repeated roots or anything like that. So it actually makes sense to use as integration points, which we'll exploit in the next chapter. Okay. Now, the last point I want to make about orthogonal polynomials is, we talked earlier about minimax polynomials, so the best approximation in the infinity norm. Now we know how to do best approximation in the 2 norm. So, what can be said about the two approaches in comparison to one another? Okay. So one thing we can say is, all right. So we use the same idea. If I define these squigglies to be the points within AB, at which the error in your approximation, f minus fn, changes sign. So what that means is, if I define pi k as I did before, probabilities linear factors, the sign changes are all canceled out, so once again, this integral cannot be 0. Kind of like what happened in the previous proof. But what that means is, k has to be strictly greater than n. Because we've already seen the error is orthogonal to all polynomials of degree n or less. So if we don't have orthogonality, we must have this. So what that means is we have some oscillation in the error. So remember with minimax, we had the oscillation theorem, that there had to be these n plus 2 critical points where the maximum error was assumed. So what we have is the error changes sign n plus at least n plus 1 times in AB. So we say that this is near minimax. So in general, the two-norm approximation of f is not as accurate as the infinity norm approximation of f, a minimax polynomial. But the thing is, most cases, we don't know how to get the minimax polynomial. We can get the two-norm approximation no matter what. So at least we have almost as much oscillation in the error as we need to. Having this n plus 1 sign changes. Okay. So, well, in fact, for a minimax polynomial, we have n plus 2 critical points. We'd have n plus 1 sign changes between them. So we have a correct number of sign changes. We just don't know if the error behaves in the other ways that we expect for minimax. But another thing is, there's one advantage. So the two-norm approximation is easy to update. If you have an approximation of a certain degree n, and you want to move up to n plus 1, because if I have fn as qj inner product of qj with f, and then I have fn plus 1 is exactly the same thing. Just going up to degree n plus 1. So that means that fn plus 1 is just equal to fn. And then we add on one more term. So increasing the degree of your two-norm approximation is a piece of cake. You can at least reuse all the work you did before, which wouldn't necessarily be true of minimax. If you up a degree of minimax, there's no reason to believe that you could just easily update minimax polynomial degree n to that of degree n plus 1. Okay. And the same is true of like Lagrange interpolant. That's not easy to update either from degree n to n plus 1. Although the Newton form, which we haven't talked about in this class, with divided differences, that can easily be updated in a similar manner to this, which is something that actually is exploited in KSS methods. Okay, so we're settling for a little bit less in the two-norm approximation compared to minimax, but at least we get some nice advantages that it's still a very good approximation, and at least it can be computed. It's very adaptable. Okay. Well, in the last 12 minutes, Brianna, would you like to enlighten us? Okay.
Oh, I have a question. I always confused which one has lesser degree, the right one or the left one?
Wait.
Because
It's commutative.
Exactly.
Yeah.
So I mean,
Okay.
if I change the place of it, then the other one will be the lesser degree.
Yeah, well, yeah, but so the thing is, you have a certain polynomial that's orthogonal to all polynomials of lesser degree. So if you take the inner product of anything of lower degree in either order, it's going to be 0.
Okay, it means that we are not assigning that exactly this one, this subscription of, for example, J is the lesser degree.
Okay.
We know that it is orthogonal to the lesser degree.
Right.
Okay.
Yeah. Yeah. So you have to be clear about how what are your subscripts and how they relate and all that.
Then there will be another problem when we're trying to find the degree, because there is like that lesser than the degree of this one, this polynomial is less than the degree of the other one. Here it does matter to place which one.
Yeah, you have to make sure you know which one is less.
So in that case, which one is less? The one which is in the right side?
Don't think about the side. It's not about the side. It's about your context and knowing which one is less. Okay, we can talk about it after if we need to.
Okay.
All right.
Okay. So I'm doing 6-3. And it basically says, given the distinct points xi, and yi. Basically, we let Q be the Lagrange polynomial of degree n for the points from I0 to n, and then R is the Lagrange polynomial for I 1 to n plus 1. So we're going to define Px as okay, and we want to show that P is the Lagrange polynomial for degree n plus 1. So it told us that Q was the Lagrange polynomial from 0 to n, so that basically tells us that Q xi is equal to yi for I 0. Similarly, since R is the Lagrange polynomial for degree n, we basically know that R xi is yi for I equals 1 to n. So in order to show that P is the Lagrange polynomial for degree n plus 1, we have to have 3 cases. So for the first case, we're going to do P x naught. And basically that tells us, we're basically plugging x naught in here. So okay. And from here, we get
Ah, dang it. Oh, wait.
hopefully y'all can read that. And so that is equal to Q x naught, which is y naught. Then we have to look at the interior points. So we're gonna suppose oh, that's okay. I have to read my own handwriting. Okay, so we have UXK and RXK is equal to YK. Because these are Lagrange polynomials. So we just plug XK in. You want me to show all of that or
Will be interesting part anyway.
let me just write this part. All over xn plus 1 minus x.
Yeah.
Should it be xk?
No, it's excellent.
Okay. Okay. So basically from here we simplify and then we can factor out, because this is yk and this is yk, so we're going to factor out yk, and we get xk minus x naught minus xk plus xn plus 1 over xn plus 1 minus x naught, and then this cancels out, and then we're just left with yk. And then we do the same thing for the case p in xn plus 1.
Yeah, but that's
We do the
actually
same
less
thing.
interesting. Than,
Yeah.
Yeah.
And basically we get yn plus 1. So since p x naught was equal to y naught, and then we got p xk was equal to yk, and p x n plus 1 was equal to y n plus 1. That basically tells us that p is a Lagrange polynomial for the points of degree n plus 1 for points xi, yi, or I 0 up until n plus 1. B.
All right.
Any questions?
So, why is it that showing that these conditions all work out, why is that enough to conclude that P really is like the Lagrange polynomial?
Because it has to satisfy it for all points I. For all points I, basically, whatever you plug in, you have to get. So basically, x n plus 1, you have to get y n plus 1 for
Or
the whole I.
how do we know there's not some other polynomial of the same degree that satisfies the same conditions that
Well, the Lagrange polynomial has to agree at the y values when you plug in.
right?
these values.
So if there was another polynomial lurking out there of the same degree that also
So basically, how do we know that this is unique?
well, we actually
So
do
we
know
have-
it's unique. That's something I covered early on, but so I won't go on to bring it up for proof of it again. But yeah, there's one thing to keep in mind. It's like the nail in the coffin that if it's unique, then there is only one polynomial that satisfies all those, and you've produced it.
Okay.
So that's the end.
I got you.
Okay. Well, that's that. Until after break.
Is that everybody?